Hello everyone, welcome back to lecture. So this is the second part. Here we will start with the basics of remote sensing, particularly the microwave remote sensing, how it can be used in seismic studies, particularly for the Himalayan glaciers. So let us try to understand the interferometry. I hope you remember this particular slide where we have explained the different part of the electromagnetic radiation. To start with, we have visible, VNIR and SWIR, then we have thermal infrared, and then we are having the microwave remote sensing region. So here in microwave we are utilizing this 0.1 centimeter to 1 meter wavelength range, right. So here we can have both active and passive microwave remote sensing, and here you can understand what is the role of atmosphere, depth of penetration and the information, what kind of information it has. So when we talk about the atmosphere, since this is the longer wavelength region, it is free from the scattering effects, right. Then comes the depth of penetration. As I mentioned in the previous few lectures, the depth of penetration is as equal to your wavelength. That is a thumb rule we follow, right. So when we talk about the depth of penetration here, it will be as good as your wavelength which you are using in the remote sensing. Then what kind of information it has? So as we have seen in the visible, VNIR, SWIR, even in the thermal infrared, we are having the information related to their chemical composition. However, when we talk about the microwave remote sensing, the more information will be related to its structure or the geometry, right. So here the chemical composition cannot be identified. However, we have other information which is required for other type of analysis that can be gathered using the microwave remote sensing. So here you can see the interferometric SAR configuration. So when we talk about the SAR, which is synthetic aperture radar, it is a system with interferometric configuration, is known as interferometric SAR or INSAR, right. So it allows to accurate measurement of the radiation travel path because it is coherent. So it is from two different position, but they are looking at the same location. Measurement of travel path variation with respect to the satellite position and time of acquisition allows to generate digital elevation model, right. So this is widely used for digital elevation model estimation or the generation. It can provide centimeter level information related to surface deformation. High resolution digital elevation model or surface change map due to earthquakes, land subsidence, glacier movement, volcanic activity and land use land cover changes are the prime application of this interferometric SAR. So the SAR interferometry needs at least two radar that you can see here. There are two radars and the radar imaging from two different places. So they are different position, right. So the phase is a measure of how far the wave has traveled. So that will be identified like this. So it is 0, 2 pi, 4 pi, 6 pi. In general, the relationship between the phase and distance is this, right. So if we have traveled by a wavelength d is equal to L, then the phase has changed by 2 pi, right. So the phase information is effectively random noise in a single SAR image because the phase are randomized by all the scattering on the earth surfaces, right. So the phase image will be like this. However, if we view from another position very close to the first, then the difference in phase tells us about the differences in the distance. So let us say this is the area and here you have one radar, this is another radar, both are looking at the same position. So if you see single image phase, so it will be like this, but when we have the measurement from two different position, so here you will have the differences in phase which can be used to identify the difference in distance. So, this is the basic configuration. Here you can see this is the arc where it is looking. So, this is the topography. Now, here we have two radars. So, this is the first one, this is the second one, and the difference between these two, that will be your normal baseline. So, here this position and this position, the difference is parallel baseline, and the difference between these two will be the phase difference, that we will be estimating using the satellite image. So, the image point is at the same location along this arc. SAR phase difference is used to point out the exact location of this, right. So, the difference between two path lengths relate to the difference in phase of the received electric fields. I hope this basic configuration is clear to you. So, the interferometry used to generate two products. The first one is the coherence image and the second one is the phase image. So, the phase image is also known as the interferogram. So, the entire image on the phase information is known as the interferogram. An image of the coherence, here you can see how we can interpret. So, coherence near 1 means the phase information is reliable. If the coherence value is less than or equal to 0.3, means the image have low correlation. So, we will consider it as noise. In this case, the phase information is not useful. So, when we say phase of a SAR signal, so here again we are having the same information. So, phase, and each SAR image pixel contains a complex signal giving amplitude and phase information of the target. So, the amplitude, it is the strength of backscattered energy which is coming from the target, and the phase, that is the last fraction of two-way travel distance, right. So, minus pi to plus pi. So, here you can see how we can calculate the phase. If the phase of the transmitted signal is 0, then the received signal covering the distance of 2r shows a phase which is equal to 4 pi r by lambda, and it will be in radians, right. So, the phase of SAR signal as a measure of relative distance, that we have understood how it works. So, a phase of a microwave signal changes as the distance between the satellite and the target changes. Consider the position of a point on a ground is changed from B1 to B2 during the two satellite passes where the displacement d is the less than lambda, right. So, here you can see this is B1 and this is B2, and the difference between these two is the d. This difference in phase is a direct measure of the difference in the length of the path from A to B1. So, this is the A, right, and which is versus to A to B2, that is the distance d. So, the d can be calculated here. So, a phase difference of 3 pi by 2 equates to a path length difference of 3/4 of the wavelength. Subsequently, we can obtain the value for d using the value of lambda provided d is less than lambda. The interferometric synthetic aperture radar, the INSAR. So, here we have seen the other diagram also where we are generating the phase information from two different positions. So, an interferogram is generated by cross multiplying pixel by pixel the first SAR image with the complex conjugate of the second one, right. So, the interferogram can be formed as this, where interferometric phase and interferometric coherence is used. So, now you have understood the basic principle of interferometric SAR. Now, how can we utilize this for the surface deformation study? So, if ground movement occur between two data acquisition, the phase changes due to ground movement is given by this relationship, right, where we are using phase change due to topography and then satellite line of sight deformation, right. So, here this is the pre movement, this is the post movement, and here the phase shift due to ground motion can be seen, right. So, the differential interferogram, this is the D INSAR, interferograms from which the topographic contribution has been removed, right. An earthquake of magnitude 7.3 occurred on 18th June 1992 near Landers town of USA. So, here is the interferogram. ERS-1 images were used to create interferogram before and after the event, which exhibited distinctive interferogram fringes, colorful contours like pattern. Here you can see these fringes, right. Each fringe corresponds to a change in distance between ground and satellite, that is about 2.8 centimeter for C-band ERS satellite, right. So, this is from this particular paper. The Lander earthquake created a large surface rupture as evidenced in the interferogram with a right lateral sweep, right. So, here you can see maximum displacement of approximately 4 meter and 6 meter at 10 kilometer and 40 kilometer distance respectively can be estimated by counting the fringes in the interferogram. So, the Big Bear earthquake occurring 3 hours later lacked a surface rupture, but was visible in the interferogram as circular fringes south of Lander, right. So, here the interferogram is very useful in earthquake studies, right. So, you have seen the interferogram how it is coming for different seismic events. The source of error in an interferogram, that also we need to understand before we go into the application. The sources of error in an interferogram primarily arise from environmental, geometric and instrumental factors, which are atmospheric disturbances, spatial and temporal decorrelation, then orbital errors, unwrapping error and the instrumental noise and processing artifacts. So, these can also introduce error in your analysis. So, when we talk about the sources of error, particularly the decorrelation, the temporal decorrelation plays a critical role here. So, it is changes in surface properties, for example, vegetation growth and the soil moisture between data acquisition, reduce coherence and affect phase accuracy, right. Then spatial decorrelation, it is caused by geometric differences in radar look angle due to baseline separation between acquisition, especially over rough terrain. A case of Latur earthquake on 30th September 1993, an earthquake struck the Latur region of India, a predominantly agriculture area dotted with small cities and villages. ERS-1 images were used to obtain a co-seismic interferogram. However, the images showed mostly incoherent result because of the change in the soil moisture. So, the main cause of coherence loss was decorrelation, which hinder effective DINSAR analysis. The earthquake occurred during the monsoon season, thus heavy rains altered surface properties, reduced radar coherence. Then the affected region is primarily agriculture, further lowering coherence. Changing vegetation and wet soil contribute to signal decorrelation. Further, cities and villages retain coherence despite the large scale destruction. Radar signal in urban environment may come from stable structures where building might remain identifiable even when damaged. So, that is the advantage of your DINSAR. So, here this is the example from Latur earthquake. So, here A is the amplitude image of the Latur region and B is the co-seismic interferogram created from 23rd February 1993 and 26 October 1993 ERS images. So, you can see here. Then sources of error, again we have the atmospheric disturbances. The atmospheric phase noises are introduced in the interferogram due to tropospheric and ionospheric path delays. And when we say tropospheric delay, when SAR images are acquired at different times with varying atmospheric condition, radar signal travel along different path through the atmosphere. So, the atmosphere will have the role here, right. It is caused by variation in temperature, pressure and humidity leading to path length differences. So, here the scattering is not considered because we are talking about the longer wavelength regions. Then ionospheric delay, it particularly affect L band SAR due to ionospheric fluctuation which cause phase shift, right. Then we have the example from the tropospheric delay and ionospheric delay. So, you can see the false topography or deformation signal due to atmospheric disturbances, and here the ionospheric effect on INSAR data that is given. Other sources of error, we have the orbital error. Inaccurate satellite position or altitude can introduce phase error leading to misinterpretation of the surface displacement. Then unwrapping error, phase unwrapping, the process of converting wrapped phase to absolute displacement can introduce discontinuities if coherence is low or gradient are steep. Instrumental noise, thermal noise and sensor specific instabilities can introduce random or systematic error. Processing artifacts, error during image co-registration, filtering or interpolation may affect phase reliability. Now, let us try to understand the seismic impacts on glacial bodies and using remote sensing how we can study them. So, analysis of glacial deformation caused by earthquake activities. So, here you can see the world map in illustrating major tectonic plates and their boundaries, and here you can see for this particular region what are the different earthquakes that had occurred, right. So, it is having the history of earthquake. So, this map is showing the Himalayan glacier, tectonic lineaments, right, Indian Eurasian plate boundaries and selected earthquake epicenters, and the epicenter with higher magnitude you can see greater than 4 we have considered here. So, the earthquake are considered based on their closeness to the glacier covered region here. So, if they are near to glacier body only then they are considered. So, the earthquake considered have magnitude varying between 4.1 to 5.7 with various hypocenter depth. These events are chosen to maximize the potential to observe the glacier seismic response through remote sensing data set. So, when we have this 2020 Tibet earthquake, here the 2020 Tibet earthquake of magnitude 5.7 having a hypocenter depth of 10 km is used for analysis. The DINSAR derived vertical displacement ranged from 0 to minus 168 millimeter indicating surface subsidence. So, the minus will be the subsidence. Glacier bodies near the epicenter showed minus 38.9 millimeter mean displacement and vertical displacement ranged from 0 to minus 79, right. So, subsidence was more prominent here. Earthquake induced surface changes varied with terrain type and proximity to the epicenter with reduced coherence near glacier moraines and lacustrine areas, while changes in peripheral glacial body remain moderate. So, that is from the analysis of the microwave data set. So, here you can see the map for 2020 Tibet earthquake of magnitude 5.7. Here the epicenters has been also considered. So, this is from the SAR and this is from the USGS, right. And here the vertical displacement is given, the influence area is marked with this boundary, right, and you can see the vertical displacement which is between 0 to minus 168, here it is 0 to minus 168 again. So, here this A, it represents the difference between pre and co-seismic coherence, and here you can see the coherence difference is between minus 0.9 to 0.97. B and C, the vertical displacements are given which is for the glacial body. So, here you can see the range, right. So, we have seen the example for the glacial bodies, how they behave during the earthquake for a particular event, and how remote sensing data sets are used in estimating their vertical or horizontal displacement, right. So, but when we talk about the glacial lake, how they behave, that we will try to understand here. So, the glacial lakes are especially vulnerable due to their high altitude, sediment laden surroundings and potential for seismic induced liquefaction. Earthquakes in the Himalayas can trigger secondary hazard such as landslide, glacial lake outburst, flood and moraine dam breaches, right. So, here you can see the glacial lakes, if they are at the verge of bursting, and that time if you have tremor, then that will lead to the subsequent hazard. These hazard poses a significant risk to downstream settlement and infrastructure. So, the earthquake can destabilize moraines and surrounding slope, potentially triggering lake outburst. Here we have understood these processes. This is calving. Because of this calving, when it falls on this, there will be overtopping, and because of that you will have the glough kind of situation, right, and the downstream. So, surface shaking reduces shear strength, especially in the fine grained lacustrine or sediments, right. Because of that you will have more vulnerability towards the glough. Landslides can fall into lake, creating displacement waves and overtop and breach natural dams. So, these are the natural glacial lakes. The actual impact varies depending on local topography, lake volume and the seismic intensity. So, role of remote sensing for hazard assessment. So, particularly the synthetic aperture radar and interferometric SAR are powerful tool to detect ground deformation post earthquake. In such situation, INSAR can identify centimeter to millimeter scale surface shift using phase differences in SAR image pairs, because we are talking about the INSAR, interferometric SAR. So, two images captured from two different locations. Optical sensors like Landsat 8 helps to monitor changes in surface moisture via indices such as TDLI that can be used, and we can identify how a particular area is behaving when we are having a seismic event. So, the remote sensing offers timely, repeatable and scalable hazard monitoring in harsh terrain that we have understood, right. So, the temporal difference liquefaction index TDLI, which is very important here. The temporal difference liquefaction index is designed to assess earthquake induced changes in soil moisture using satellite data. So, utilizing SWIR band, which is between 2.11 to 2.29 micrometer, which are effective in detecting variation in soil moisture. The TDLI is calculated using pre and post earthquake reflectance values to identify possible liquefaction prone zones. This method enables large scale non-invasive assessment of seismic impacts on terrain stability in high risk glacier and sedimentary region. So, this without reaching to that particular location, you can have such analysis which will provide you more information about the vulnerability of that particular area towards the earthquake. Temporal difference liquefaction TDLI can be defined as this, where we are using the SWIR wavelength region. So, the positive TDLI value indicate an increase in soil moisture, suggesting potential liquefaction or cyclic mobility near glacial lake margins. Negative value represents drying or reduced moisture, typically implying lower seismic induced instability. Combined with coherence analysis from SAR data, TDLI enhances the reliability of seismic impact assessment around glacial lakes. For example, 5.7 magnitude Tibet earthquake which occurred in 2020. So, we have used the interferometric SAR and then we have identified how vulnerable, what is the impact of this seismicity on this particular area. So, this is one example from Tibet earthquake which occurred in 2020. So, here we have combined this SAR data with the TDLI to identify the seismic impact on the glacial lakes. So, combining these two will enhance the reliability, right. So, here the map showing pre and co-seismic coherence difference and TDLI values. This is another example from Gorkha earthquake 2015. So, here you can see the over 4,300 co-seismic and post-seismic landslides were recorded, but no major globs were observed. The spatial distribution of landslide closely correlated with slope, peak ground acceleration and geologic structure, and here you can see the locations are marked Kathmandu, Gorkha, and here you can see the moment magnitude is 7.3, here it is 7.8. Remote sensing played a key role in rapidly mapping affected region and assessing the risk evaluation. So, long term monitoring and risk reduction. So, the continuous satellite monitoring enables detection of evolving risks in glacier region, and we all know how important it is to monitor the glacier and the snow areas. Integration of SAR, optical and DEM data allows multi-hazard assessment post earthquake. Early warning system for GLOF rely heavily on near real time remote sensing updates, because we are trying to bring all the real time data sets so that our model will be more accurate and it will be predicting the near future hazards. Regional hazard zonation supports planning and emergency preparedness in vulnerable areas. Seismicity particularly, it poses a multifaceted threat to glacial lakes through direct shaking and cascading hazards. Remote sensing technologies have revolutionized how we detect, monitor and assess such impact. Case studies from Nepal and Tibet demonstrate the potential and challenges of satellite based hazard analysis. Continued research and technology integration are vital for mitigating future disaster in the Himalayan region. These are some of the references that we have used in this particular lecture. So, if you are interested, you can refer to these papers. You will find more detail about the impact of seismicity on glacier bodies or glacial lakes, and how remote sensing, particularly the microwave remote sensing data sets, are used to assess the impacts. Thank you very much.